Okay, so I just wanted to begin with a clarification of our units on the x-axis here. So we can really look at this two ways. And here in purple we've got y equals the sine of t or y equals the cosine of t are typically called vibration graphs, and one oscillation is called the period, and I've graphed one oscillation on each here down below. So if we're going to look at it as a function of time, then our height y of the wave is going to depend on time, and that's in seconds per cycle. Seconds per cycle. Okay, or another way we could look at it is here in red, which is y equals sine x or y equals cosine x, which are called waveform graphs, which is maybe more typically of what we're looking at in this section and chapter. And one oscillation is called a wavelength, but it could also be called a period. They're pretty interchangeable. Also called one cycle. Okay, and in this case, our x-axis, instead of being time, is distance in radians, in radian measure. So we can look at the height of our wave as a function of horizontal distance, or we can look at the height of our wave as a function of time. So depending on the situation we're modeling, we can look at it both ways. Okay, thank you. Okay, let's talk a little bit about radio waves and this idea of amplitude modulation. So, anytime there's an electric current or voltage, then it's going to create an electrical field around it. So, anytime we have, say, electrical current, it's going to create this field, and the field looks something like that. Now, maybe you get a parabolic dish here, and then you can what's called propagate these waves, is you send them out. You propagate, you take that electric field, it generates a wave, and the parabolic dish helps send out that wave. So if we're dealing with, say, amplitude modulation, which you're dealing with, say, with AM stations, well, if I were just looking at sine of x, well, this is our typical sine of x graph. Well, maybe we had on our next period, and there's the period, 4 sine of x. Well, that would change what's called my amplitude. Over the same period, it would essentially make my amplitude larger. So larger amplitude is essentially just a stronger signal wave. So what happens in amplitude modulation for radio waves is that essentially the amplitude is changed or modulated as it's sent out in order to communicate different sounds, which then are interpreted by a receiver on the other end, and they come out as, say, a weather alert. Okay, so maybe they amplify the next period even more, maybe up to 10. Okay, so they've taken, so the period stays the same. In this case, we just did 2 pi each time. For amplitude modulation, say AM radio, they're not going to change the time it takes to make one cycle, but they are going to change the amplitude, in other words, the strength of the signal. And by making it either stronger or weaker, they can what's called modulate it. And that modulation is what actually communicates the information that is then translated into sound. Now keep in mind, these are not sound waves that are traveling through the air, because sound waves travel much too slow. These are what's called radio waves. They travel at the speed of light. So this signal of energy has within it, and it's called a signal wave. It has within it this amplitude modulation, which essentially carries the signal. It carries the information that's then interpreted by the receiver that then's translated into sound. So the radio wave moves at the speed of light, it's interpreted, and out comes the sound. And that information is attached through modulating this signal wave. Okay, let's continue with our discussion of radio waves, except this time let's look at frequency modulation. And we're going to look at the two graphs, y equals sine x and y equals sine of 4x. Now, notice the period on y equals sine x here, which is 2 pi over the absolute value of b, and of course b is just 1, that's found in front of the x, would be 2 pi. In other words, the time it takes to do one cycle or one wave is 2 pi. Okay, so we have a frequency of one wave per every 2 pi. Now, if we look here at y equals sine of 4x, and again, I put the same period length here of 2 pi, well, notice my period would be 2 pi divided by the absolute value of b. So the absolute value of 4 is 4, 2 pi over 4 is pi halves. So the period length shrunk on this graph to pi halves. So when the period went down, well, what happened to the frequency? It went up. They have an inverse relationship. So remember, our frequency equals 1 over our period. Okay. Okay, so notice when y equals sine of 4x, if I looked at, say, the same 2 pi on both, well, this one completes 4 waves for every 2 pi, and this one completes 1 wave for every 2 pi. And let's put here pink frequency equals 1 over the period. And that makes sense because it has that quality of y equals a over x, which remember they have an inverse relationship. So when my period shrunk from 2 pi to pi halves, in other words, it went down, well, the frequency went from 1 wave to 4 waves. It went up. Okay? So the shorter the period, the higher the frequency. The longer the period, the shorter the frequency. Okay, so what's going on with frequency modulation on your radio dial is your amplitude here is going to stay the same. Notice. But what's going to be modulated is what's called the frequency. Well, how many waves did it do over this first section of, say, 2 pi? Well, it did 1 wave. How about over this next section of 2 pi? Well, it did 2 waves. And over the next section, maybe it did 4 waves. By then modulating that frequency, that signal wave coming from, say, the radio tower up on the mountain is going to be able to broadcast. Essentially, it's going to translate that information from that frequency modulation into sound. Okay, remember, the actual radio wave is not sound. The actual radio wave is travels at the speed of light and is essentially energy directed by a dish and received by a dish. But the actual modulation, the frequency modulation, is what's going to allow for more of that information to be communicated. Okay, so what are each of these good for? Well, amplitude modulation is typically good for long distances. It travels to remote areas and it travels across continents. It's good for talking, but it's bad for music. It'll typically create a long, big wave. Okay? And that wave can even travel through mountains. And it travels long distances. So if you need to send out an emergency message across the whole continent, well, use amplitude modulation and you can send it out there. Now, FM or frequency modulation came later, and that's better for music because it gives you a clearer signal. And typically it's got a shorter wavelength. And usually you need to elevate it so you can direct it, say, down into cities or into a geographic area, right? This is my mountain, and that's my signal up there broadcasting. Okay, whereas AM typically, amplitude modulation typically needs to be grounded on the ground, maybe at the edge of the continent, and there you're going to use usually bigger dishes even than that, okay? Okay, so just to wrap up, I wanted to do a little video to show some of these applications because I often get the question, but what do we use it for? And well, with the sine wave, I almost feel like saying, well, everything. So your cell phone is dealing with, say, a type of wave, like a radio type wave, and speed and bandwidth, of course, are related. Your speed depends on how much information you can include in the signal, aka your bandwidth. Or television, satellite communication, a radio telescope to let us see into outer space. These are all forms of really radio waves, including, say, something like a microwave oven when you heat up your burrito. And then, of course, light and sound, while they're not radio waves, they're also take that sinusoidal shape, the waveforms. So these sine waves are passing through your house and your life all the time, and I just wanted you to be more aware of the applications of this material you're learning, which are myriad. Okay, so I hope you enjoyed the video. Have a nice night. Bye.